Indeed, this is Amit Varma, and Adiola is part of this presentation. I hadn't expected that, and Jungil Su. Jungil, I've always butchered your last name, but that's the best I can do. Breakout of fully developed reinforced bar anchors in concrete experimental testing. This is work that I've been associated with. I find this to be really compelling, and so I hope you see it the same way I do. With that, Amit, the screen should be yours.
Thank you very much, John. I really appreciate the opportunity to make this presentation. I want to tell you an interesting story, one that has been developing over the past 5 years. Now, to some, this story is going to be run of the mill, and to others, it's going to be a thrill ride, and to some, it will be a horror story. Nevertheless, I believe this is a story that must be told, and so here I am, making this presentation to you. Now, like any story, there are many characters and contributors to the story. There are sponsors like Westinghouse, KEPCO, SNERDY. There are organizations supporting this work like the ACI 349 committee, which has been driving this for a long time. And that's why the acknowledgements to Adiola, she's our current chair. And there are universities where tests have been conducted, like Purdue University, from where my co-author, Professor Jungle So, and his students, Ata Rahman and Hassan Anwar, are a part of. Tongji University, where we had great collaboration with Professor Zhao, and Incheon University in South Korea, where the tests were conducted by Professor Chon. There are also individuals involved with this. Professor Rachel Cheeky, she's now at Cincinnati. She has contributed a lot to this work. And of course, John Silva, who's been sort of the shepherd all along. Adiola, of course, from Bechtel. And then there have been some contributors recently from the University of Stuttgart with Professor Sharma and his PhD student, Marga. These individuals are perhaps the most important because without their contribution, efforts, and passion, this story would remain incomplete. So let's start at the very beginning, perhaps 5 years or so ago, when conventional wisdom dictated that groups of straight reinforcing bars that are fully developed in the concrete will develop their yield strength before pullout. The concept of development length reigns supreme. Development length, of course, is a higher level concept that deals with several lower level failure modes implicitly. When asked about groups of straight reinforcing bars undergoing failure modes such as pullout, breakout, etc., conventional wisdom would dictate that is not an issue. It is not a problem. Unfortunately, I found myself in a tricky situation, performing a design review of a situation consisting of embed plates that were anchored into concrete with groups of straight reinforcing bars. Luckily, John was on the same review panel, and we found ourselves in the minority, arguing against conventional wisdom, which is never a good idea. There were differing opinions in the room, but the regulatory environment was extremely conservative and touchy. From a safety perspective, since no one could point to relevant test results, we prevailed, and the design considered breakout limit states for such a design. However, it raised questions about, causing difficulties for the community by conjuring limit states where none existed. Or in simple words, does a tension breakout failure mode exist for a situation shown here, consisting of an embed plate anchored into concrete with groups of fully developed reinforcing bars? I also want to point out at this point that there are two types of reinforcing bars that we'll be talking about throughout this presentation: deformed rebars and, of course, deformed wires, which are cold drawn as well. Both of them will be included. So we decided to do exactly what a hard-pressed structural engineer would do. We planned to do a test to investigate the potential breakout failure mode. Now, since we didn't have many funds at that time, we decided to build two small-scale specimens with number 3 deformed wire anchors. The embedment length was greater than the calculated development length, we built two small specimens, one with a 2x2 configuration and another one with a 5x5 configuration. The spacing is noted there, and the names of those specimens are also included. The initial results were promising. The 2x2 configuration of straight bars developed the tension strength of the rebars, and there was no breakout failure. But this was also expected according to our pre-test calculations. You're actually seeing a picture of that deformed wire there, and the fact that the failure mode was such that the steel had developed its complete tensile strength. Very promising, but also estimated with our prior calculations. When we went to the 5x5 configuration, the test results were quite interesting. This is just a photograph or a drawing of the specimen that we were looking at. Before the steel tensile strength could be achieved, we got what was a concrete breakout failure and a breakout cone that separated from the concrete. This was the first time such a breakout failure had been observed, to our knowledge, within the realm of our limited range of experimental data that we were looking at. But it was quite significant. The steel did not develop its yield strength. Instead, the concrete developed a breakout failure. However, there was a flag on the play. There was a concern that the test was small scale, using deformed wire anchors, and surely this was not going to occur in a large scale specimen with deformed rebars. So we did what any structural engineer would do. We decided to conduct 4 large-scale tests with straight rebars, deformed rebars, and also deformed wire anchors, with the embedment lengths greater than the development length. And in this case, we selected number 6 rebars and deformed wire anchors. We selected a 5x5 configuration. You'll see very quickly that the specimens become extraordinarily large. This was the test setup that we used in order to conduct these large-scale investigations. There were fewer tests because they had become quite large. If you think about it, the breakout cone, if it were to develop, would be about 3 times the embedment length, which itself is greater than the development length. And then while we're doing the tests in the laboratory, we don't want the tie-down points to interfere with the breakout cone. This is a photograph of the test setup with the concrete block and the hydraulic actuator, the sensors, etc. Here's the photograph that you're looking at. You can see the sensors, the sensor arrangements, the actuators. And we try to make sure that nothing interferes with the breakout cone if one were to develop. So we conducted the tests, and both specimens with the deformed rebar anchors, the 5x5 number 6, both of those specimens developed breakout failure modes. And I'm showing them here to you from both tests 1 and 2. As you can see, the embedment length of the bar was approximately 2 feet, and the range of the breakout cones was in the neighborhood of about 36 to 40 inches, which is what one would expect if breakout were to develop. The deformed wire anchors, which are the ones that are slightly different from the deformed rebars and have the dimples on them, they had an embedment length in this case of about 27 inches, and we saw the same sort of breakout cone develop with a range going, as you look at it on the top, you're seeing about 36 to 41 inches and so on. All 4 specimens illustrated the formation of this breakout failure mode. So what we did was we pulled out that breakout cone from the concrete, and it became quite an interesting sight. We wanted to examine some of the cone angles, etc., just for documentation purposes. But we also found the photographs to be quite compelling. And we also calculated, or back calculated in this case, what would be the effective K value for the deformed rebars, which from those tests we found to be 35. And for the deformed wires, we found the effective K factor to be in the neighborhood of about 30. The photographs were quite spectacular and definitely worth 1,000 sketches of a breakout failure mode. And they've been seen multiple times in different committee settings. There was one more advantage of this large-scale test. We actually got a chance to compare our small-scale test with the large-scale test. So we were able to put the two tests next to each other, the half scale and the full scale. And as we compared them, we noticed that they were quite similar to each other in terms of the breakout failure mode, the effective value of K, and so on. This gave us the opportunity to conduct slightly smaller scale tests because these huge specimens were quite huge in order to get rid of from the laboratory, rather than at full scale, which can be quite cumbersome and also cost prohibitive. So then the question was, okay, the initial objection was resolved, which was related to the small scale. And so the question became, what is the K factor? And we could draw sketches of these breakout failure modes and talk about it in settings and say, okay, we can calculate it, but we need an effective value for the K factor and so on. These are your common breakout equations that you are familiar with. And the question became, what would be the value of K? So looking at some of the existing literature, we found that when you're working with mean strength predictions for cast in place, you're looking at an effective K factor of about 40. For post install, you're looking at an effective K factor of about 35. So at this time, there was another flag on the play, and there was insufficient test data to have an effective value of K and actually be able to conduct a reasonable statistical analysis. So by this time, we had presented all this information to the 349 committee, and the committee was fully on board. And so we decided to embark on a comprehensive, coordinated testing program with members from China, South Korea, and other countries wanting to help contribute and participate. We decided to consider both deformed rebars and wire anchors and include different sizes and spacing. And we came up with a very big test matrix that we then broke up into 3 pieces and sent it off to different parts of the world in order to get experimental data. Now, the story up to this point is documented in the publication listed here by Professor Cheeky. It has been co-authored by the team from Purdue, but you can read the story up to this point in that paper. The story here onwards is investigations as they are continuing in the US and in other locations. So here in the past 1 year, we've conducted about 8 tests. Actually, we designed and coordinated a test program and requested funds from the ACI Foundation a couple of times. After the lack of success, our international partners decided to step in and help. The work in the US was partially funded by KEPCO and partially funded by Hilti. The work in China was funded by SNRD, and the work in South Korea was also funded by KEPCO. The US test matrix included a couple of specimens with number 5 rebars, but the rest were all with number 4 and number 5 deformed rebars, and I explain that in a little bit. We used configurations of 5 by 5 and 3 by 3, and the spacing of the bars was also included as a parameter. This was all happening in 2019, which, as you know, was a difficult year for trade relations, especially with China, and that made a play in how our test matrix had to be divided up. This is a photograph of the test setup in the Bowen laboratory as we were looking at conducting these tests. You can see it's the same setup that we had used earlier. The blocks were a little more manageable, but they were still quite big. As we were conducting these tests, we had sensors for measuring the behavior of the strain gauges in some of the rebars in some of the specimens. We tried to use the same setup for all the tests in all the countries, as you'll notice. So we found from these large-scale tests that we continued to get consistent breakout failure modes. And we continued to pull those cones out after failure so that we could have some pictures and make the point on what it is that we were observing. But before I move on, I want you to get a sense for how this experiment really goes and what kind of a brittle failure mode this really is. Now, you can't hear the sound because the sound is playing in my headphones, and I should have thought this through earlier. But I'll play the video again just so you get a sense for how quickly, this is a real-time video, how quickly this failure occurs and how brittle this failure mode is. It's important to note that our hydraulic equipment actually cannot keep up with such a brittle and rapid failure mode. So the post-peak descending branch of the measured load displacement curves is to be treated carefully. And that's something that we are aware of as experimentalists. This slide summarizes the results as they are now complete, at least on the US side of things. We were able to fail the specimens, get breakout failure for most of the experiments that we had conducted, and back calculated an effective value of K. Those effective values of K are shown here, and you'll notice that they're in the range of about 30 to 39 or so. We had a couple of specimens where the spacing, when it's increased from 3 to 4.5 inches to 6 inches, that you get different failure modes eventually developing the full strength of the steel. But we also conducted a portion of our tests in China. They were conducted at Tongji University. Now, because of the limitation on the trade with China and the steel tariffs that were imposed, the initial test matrix that we had proposed could not be conducted. They couldn't get the deformed wire anchors, and it was difficult for them to get US rebars as well. So they ended up having to do the tests on US rebars that were purchased in China. Overall, the test program was quite successful. You'll notice that the test setup is almost identical to the one we used in the US. The hydraulic equipment, the sensor layouts, and all of them were quite similar. And that's because we had gone over to interact with them and make sure that the tests were going to be useful for our committee to deliberate upon. We were there for that first test where they got that breakout failure mode that you can see the student is pointing to in China. And again, we suggested them to pull out the cone, which they did, and made pictures of what it would look like. And then on the bottom there, you'll see a picture of Adiola, our chairman, committee chairperson, out at the test in Tongji University in October 2019. And yes, it was before the pandemic, when we used to travel to places far away in order to go do research. And it was in Shanghai. This is the summary of the test results from China. As you can see, they tested mostly number 4 and number 5 deformed rebars. They used 3x3 configurations and 5x5 configurations. And they got breakout failures in most of the cases. They attributed that their yield strengths of their rebars was quite high. Anyways, the back calculated value of K effective was also a bit on the high side. It ranged from about 40 to 45. We're trying to collect more information from the Chinese researchers to understand what the results and what could potentially be the cause of the slightly higher K effective. But this slide actually summarizes a compilation of all the tests that were conducted using deformed rebars. This includes the original tests by Chiki, by the current tests that were conducted at Purdue, and the recent tests that were conducted at Tongji. You'll notice that we've included number 4s, number 5s, and number 6 rebars, different configurations, 3x3s, 5x5s, and so on. And after compiling all those results, we were able to obtain a summary of the effective K values that were calculated from the results in US and China, including both old and new. And we were getting an average effective K value of about 39.6. If you assume a K effective to be 35 instead, then the median strength ratio is shown there to be 1.13. Investigations were also conducted in South Korea, but there they were focusing mostly on the deformed wire anchors. They conducted 13 tests. The deformed wire anchor diameter was the number 7. You're looking at the different embedment lengths and spacings that were used. Their test setup was a little bit different than ours, but their overall behavior was quite consistent. They had some, as you can see on the right-hand side, you see a photograph of the embed plate with the deformed wire anchors, and you're also seeing some protrusions that were used in order to pull the specimen upwards in order to simulate the tension effect. The breakout failure modes and cones they obtained were comparable to the ones that we obtained in US and in China. depending, of course, on the development, the embedment length that you're looking at over there. They were nice enough to share this data with us for committee deliberation purposes. And we compiled all the results for the deformed wire anchors and looked at the summary of the effective K values. We found that the effective K value for all the tests that included all of the tests initially done by Professor Chiki, the tests that were recently done at Purdue, and all the ones that were done at Korea, the effective K value for these deformed wire anchors was about 36. If you assume the K effective to be 35 in the calculations, then the median strength ratio is about 1.03. So here we're slowly getting to a stage where we can now bring this story home and get some closure on this topic. So here is the proposed equation for estimating the breakout strength for fully developed straight bar anchors. We're currently proposing an effective K factor of about 35. It gives you a sense of what this looks like. This was a proposal that we were looking at as part of the committee and thinking about how to approach it. But there's another topic that we are thinking about as we are looking at this problem, and that is related to the bond strength. While it is evident that we get breakout failure modes from all of these specimens, we're also wondering about the bond strength of that group set of anchors. Now, this is a topic under discussion, and while we don't have answers yet, we are actively thinking about how to approach the problem. What you're seeing here is the equation for bond strength for a group of straight anchors. And what I've highlighted in that circle there initially is the tau bar, that's the uniform bond multiplied by the perimeter length of each individual bar. And then that is multiplied in order to account for the groups with a function of S critical. And this S critical value depends upon the uniform bond stress, tau bar, that is associated with the particular type of reinforcement that you're using. For normal deformed reinforcing bars, we find tau bar to be about 1450, and for wire anchors, we find it to be about 870. One thing that I did not include in this presentation today was a whole series of pull-out individual bar tests that were conducted in order to experimentally obtain the value of tau bar. Those were conducted in the US, in China, and also in South Korea. But getting into that detail would take a lot more time. And anyways, this is a story. This is the part of the story that is under development. One thing that we're particularly looking at is the group effect for calculation of this bond strength that we're trying to assess as well. And this is active work that's ongoing. Another important development was to gain additional insights into this failure mode and its mechanics. So developing 3D finite element analysis using different tools, for example, LS-DYNA at Purdue and MASA at the University of Stuttgart, became important. In LS-DYNA, we are building models using concrete elements, bond behavior, and CEB FIP recommendations for the models for the bond stress slip curve and the concrete tension versus crack opening displacement and so on. Just to give you a flavor for what this looks like, this is a photograph of the LS-DYNA model that we've built for some of our specimens. The results and comparisons are quite encouraging, but the models take a lot of run time. With elements as small as 1 inch in such a big foundation that we are pulling on, it's quite a bit cumbersome. But the breakout strengths that we are calculating are within plus or minus 10% of the experimental value. When you look on the right-hand side there, you're seeing a comparison of the FEM, force versus displacement response. And post-peak, when that breakout failure occurs, clearly the experiment is not going to be able to give us a reasonable value because of the issues with the hydraulic control. But similarly, the FEM, depending on whether you're using load control or displacement control, can give you different post-peak branches. And that's why it's a dotted line. Really, it's a comparison of strength that we're talking about. And at that point C, where we're talking about the peak strength, we are looking down or drilling down further and looking at the stress contours, the principal strain plots, trying to gain additional insights and a deeper understanding into this phenomenon of breakout failure along with the bond failure so that we can put the story completely together. Additional ongoing investigations, we've started international collaborations with the University of Stuttgart that has been very helpful. with Professor Sharma and his student Marga, who are using massa to model the experimental behavior and provide unique insights into the behavior. It's really fun for us to see how these very different models, LS-DYNA models are very different from massa models, are based on completely different numerical approaches, are comparing with each other and showing overall behavior that is similar to the experiments. Pre and post analysis is being conducted using FEMAP. The massa models incorporate nice meshes with small tetrahedral elements that are accounting for the behavior. And they are being able to identify some of these failure modes and pull-out cones and multiple failure crack surfaces that are originating as the structure is being loaded. There's a lot of potential for us to be able to explain the interaction of the bond and breakout failure mechanisms from these numerical models. In summary, I'd like to tell you where we are at in the story now. Breakout is a real failure mode, particularly for groups of straight reinforcing bars or deformed wire anchors. Now, this is particularly applicable to embed plates in concrete, however, suggests that other situations may need to be considered and thought through. The K factor for breakout strength is equal to 35 for a mean prediction. The model for bond strength still needs a bit of tuning, and we're working on that. And the numerical models can help provide additional insights into the overall behavior. That's the story that I wanted to share with you today. I hope it was informative and at least useful for some of you.
Perfect. Thanks, Amit. We have a couple of questions that came in on the box. I don't know if you can see them in the Q&A.
I can. The question was, first question is, were broken aggregates used in the tests in Tongji? And the answer to that question is, I'm not familiar with exactly which aggregates were used. We did share them, the mixed design, but I don't believe that they had used broken aggregates. Another question is, does the type of aggregate, rounded versus crushed, or its stiffness affect results? That's an excellent question. I don't think I'll be able to answer that right now, because we need to consider, in all the tests that we did, we used a specific type of aggregate. It's something that I need to take into consideration in the future. But that's also another question that we can ask to overall breakout failure modes, whether the type of aggregate has an influence and how much does it affect the results.
And somebody wants to know how many days it took to run LS-DYNA.
1-inch elements using LS-DYNA. We have some really good servers that are dedicated to doing our simulations. I think it takes about half a day to run the full simulation. Sometimes we'll run a quarter model just so that we can be sure that we got all the parameters right, and then we'll run the full one to get the nice pictures that we were looking at. And that may run for a whole day.